All right, so in this video, we're going to talk about what Merkle trees are. This can be a very complicated subject, so I'm going to attempt to make it as light as possible and as straight to the point as possible. So we're going to talk about what a Merkle tree is, why we use them. I'm going to give you guys a few examples, a couple of examples, more visual examples, so you can understand why Merkle trees are important and how they actually work. And I'm going to give you guys a quick conclusion at the end. So, what even is a Merkle tree? A Merkle tree is a hash tree where every leaf node contains the hash of a specific data block. In blockchain, this tends to be a transaction. And every non leaf node contains the hash of its children. The root, which is called a Merkle root, and every single Merkle tree has got its own Merkle root, is a single hash that cryptographically represents the entire data set. If any piece of data changes, the root changes completely, which makes Merkle trees an elegant and tamper-evident structure. This is super important because we use Merkle trees to prove that a specific piece of data is within that data set. So let's actually have a look at what a Merkle tree looks like. These are the data blocks here in the bottom. And in a blockchain, for example, Ethereum, each data block would be a transaction. Every transaction would get hashed. And if we pair the hashes of the transactions, we would get to our non-leaf nodes. These nodes in the bottom are what are called leaf nodes. These ones between the leaf nodes and the Merkle root are called the non-leaf nodes. And the top hash, which contains the hash of every single node within that Merkle tree, is called the Merkle root. So why would we want to use Merkle trees in Ethereum specifically? They provide a very, very efficient verification because by using Merkle proofs, light clients don't need to download the entire blockchain to verify a transaction. This is extremely important. Imagine we have millions of transactions, million pieces of data. We don't want a client to download millions of bytes in data to be able to verify a single transaction. That wouldn't be efficient and it wouldn't be scalable. So with Merkle proofs, we can actually do that in a much more efficient way because a Merkle proof is enough to cryptographically confirm that a transaction is included inside of a block. And like I said, we use them for tamper detection. The Merkle root acts as a fingerprint for all transactions in that block. And if a single byte in any transaction is altered, if anything inside of that Merkle tree changes or someone tries to change a piece of information, the root changes completely and we would be able to verify that indeed that Merkle tree has been tampered with. And this makes any manipulation immediately detectable without inspecting individual transactions, which again is extremely important if we want to scale it, because we wouldn't want to check every single transaction to see if it's been tampered with. We can just have a look at the Merkle root and verify that indeed it's the same Merkle root as expected. So let's take a look at an easy and visual example of a Merkle tree. And it's this very, very simple example. Here in the bottom, we've got our leaf nodes, and it's just numbers 1, 2, 3, 4, 5, 6, 7, 8. In the real world, you wouldn't have numbers, you would have hashed data. And what a Merkle tree does is it pairs these leaf nodes and it hashes them together. In this case, we're going to sum them up just to make this example way easier to understand. So in this case, we sum them up, but remember that typically we hash them together. And in this case, we would have 1 plus 2 equals 3, 3 plus 4, 7, 5 plus 6, 11, 7 plus 8 is 15. Now, again, we group these non-leaf nodes in pairs of 2, and we would sum them up again. 7 3 is 10, 11 add 15 is 26. And again, we would pair these two nodes and sum them up together, and we would get to the Merkle root, which is 36. Now let's have a look at why we are able to prove with just a bunch of nodes that a specific, in this case, number is inside of this Merkle root. Because let's say we want to check that 8 is inside of the whole Merkle tree, we have two options. We can either download the whole Merkle tree, which is not optimal, like I said, or we can use a Merkle proof, and just by getting the numbers 10, 11, and 7, we can actually verify and see if number 8 is inside of this Merkle tree. So how would we do this? We just need to basically take away 10 from 36. So if we do 36 minus 10, that is equal to 26. So we only need the root number 10 to verify that this is 26. Now, remember we got given number 11, so 26 minus 11 is going to equal 15. And we also got given number 7, so 15 minus 7 is going to be equal to 8. So with just these three numbers, 10, 11, and 7, we can verify that number 8 is always, or in this case, is inside of the Merkle tree. Now, take into account that we will always have the Merkle root accessible. That is always accessible, so we can always know what the actual root is. And just by getting these three numbers, we can verify that number 8 is inside of this Merkle tree. Obviously, this example is very silly because it's just a few numbers, but imagine we have millions and millions of numbers or million pieces of data. You wouldn't want to download all that data just to verify a single number or a single transaction is inside of that data set, inside of that Merkle tree. You will want to get specific nodes to be able to verify that, hey, okay, this transaction or this piece of data is indeed inside of the Merkle tree. So I hope that makes sense. And just to prove to you guys that a Merkle tree is a tamper-proof system, what happens if we change this number 4 to a number 5? So as we can see, we change the number 4 to a number 5, the whole result of the root changes completely. So this is what I meant when I said that if you change just one single piece of data, the root will completely change and we will be able to see that the evidence has been, or the data has been tampered with. Why? Because we're expecting a root of 36, but in this case, we're getting a root of 37 because we changed this piece of information here, this node, from A4 to A5. So, in conclusion, Merkle trees are one of the foundational data structures that make Ethereum, blockchains, and just computer science really in general, but we're talking specifically about Ethereum. It makes Ethereum trustless and scalable. Like I said, it's not very convenient that you have to download every single piece of data. That wouldn't be scalable. It would be very, very expensive and it would just not make Ethereum scalable at all. By reducing verification to a handful of hashes, they allow light clients to participate in the network without storing the full chain. This is extremely important. You don't want to use a lot of computational power to basically get just one piece of data. It is not scalable. Okay. And with Merkle Trees, which is a new version, an enhanced version of a Merkle tree, let's call them that for now. It is very, very new. So with Merkle trees on the horizon, proof sizes shrink even further. So this will make Ethereum even more scalable and more usable for every single client out there. So anyway, guys, thank you so much for watching this and consider subscribing if you found this helpful, and I will see you in the next one.